the 4 bytes for the checksum. So we can now send these packets, or we can send 16 fragments. The protocol allows up to 16 fragments of a packet with 4 bytes of chosen plaintext in each packet. And what happens is the access point will combine these fragments into one single packet, because it can send larger packets, and will relay that packet. And if we capture the relay, we now suddenly know 68 bytes of key stream, which are 64 bytes, 16 times 4 bytes from the fragments we sent, plus the 4 bytes of the checksum of the plaintext. So this can be used for discovering large key streams. The next attack you can do with that is you can do real-time decryption. After you have discovered a large key stream, you can generate arbitrary packets. And in IP packets, the routing information is only located at the beginning of the packet, the IP header, and it's routed according to the destination address. So what we can do is we can generate the first part of a packet and put some routing information in there, which means that the packet should be routed to us, for example, to our web server. And then we send this packet, which is just the beginning of a packet with routing destination our web server, and we can then send another captured packet we have received on the network as fragment number 2. So what happens is the access point will take both fragments, build a single packet out of these, and send that over the internet to us. Because both packets are valid, and we get no problem with encryption and decryption, because we are able to encrypt arbitrary packets, which includes this IP packet, and the other packet we have received is correctly encrypted too, because we get it over the valid network. And we don't need any mathematics or cryptanalysis skills for that. It's just a design flaw in the protocol. We can just edit the fragmentation information and therefore build new packets out of fragments. And this is nice because it allows us to decrypt a single packet in less than a second, because we just have to send one packet which contains the routing information that it should be sent to us, and then we have to inject a captured packet again and label it as fragment number 2. And this works very fast. Only problem is some vendors tend to implement fragmentation not so correctly, so this means this attack doesn't work on some buggy access points. Well, and there are some other tricks too you can do using this method to do other things like real-time decryption, like the Chop-Choke attack or so. Last attack I got will be the PTW attack. Basically, what happened was in 2004, the best attack on WEP was the Coric attack, which allowed you to discover the secret key with about 500,000 packets sent and received. And this was possible, and because you can send about 800 packets, you can receive about 800 packets per second from a fast network, sometimes more. And so you need a little bit more than 10 minutes to discover the secret key. And in 2005, Andreas Klein showed analysis of the RC4 stream cipher, which is used in WEP, and he had a theory how to alternatively break that stream cipher in WEP-like modes. And in 2007, we started looking at this analysis, and in April we had first implementation of our attack finished, which was now able to attack WEP with only 40,000 packets. So what you could do with our tool was to discover the secret key of the network with just 40,000 packets, which means if it's a fast network, you can do it in less than 60 seconds. So what you do in our attack is you are injecting ARP packets back into the network you have once sniffed, and then you are reading the replies, and you can discover most of the keystream of the replies because ARP requests and replies are always constant in the first 15 bytes, and therefore you can rebuild the keystreams of these packets. And the exact number of packets depends a little bit on the exact structure of the key and how much luck you got on the, for example, it depends on the IVs which were chosen, but all methods which are currently implemented in access points usually tend to generate IVs which make it possible to decrypt the key with 40,000 to 85,000 packets received. So let's have a look at the stream cipher which was used in the WEP protocol. It was invented in 1987 by Ron Rivest, RSA Data Security, and it was kept as a trade secret and sold commercially to people which were interested in fast software stream ciphers. And in 1994, the source code of RC4 appeared on the Usenet, and from now on, RC4 was completely open. And it's very common in use, and it's very efficient, so you can implement it by just doing random access to memory and only 8-bit addition. That's everything you need to implement RC4, so you can do it on real small hardware, or and it's even fast on modern PCs. For example, it's used in SSL TLS. Source code of the cipher is really short. RC4 consists of 2 algorithms. Can you read that? Who can not read that? Okay. RC4 consists of 2 algorithms. First is the key sketching algorithm, which initializes the RC4 stream cipher from an arbitrary length key k, which can be somewhere between 8 bits and 2048 bits. And generates a more or less random permutation from this key. So RC4 is an internal state of a 256-byte array S, which always forms a permutation of the numbers from 0 to 255, and 2 integers E and J. And after this initialization has been done, you can generate a key stream of arbitrary length from these values by just repeatedly executing these operations, which will generate a key stream bitewise from that permutation and these integers and update the permutation. And for the rest of the slides, I will use the following notation. Sk is an initial permutation S after exactly k swaps have been executed on S. And J is the same, is the value of J after k swaps have been executed on S. And S to -1 means the inverse function of S, or the inverse permutation. So we got this for loop here, and in every iteration of the loop, 2 values in S are swapped. And we will have to look at the swaps which happens inside S. And in a WEP scenario, we know that the key used for a packet always consists of 3 bytes initialization vector and a secret root key, which means that an attacker always knows the first 3 bytes of the key, which is used to encrypt the packet, and he can therefore look at the first 3 swaps on the RC4 stream cipher, because the first 3 swaps which are executed here only depend on K0, K1, and K2, which are the first 3 bytes of the key, which are the initialization vector in WEP mode. And we must assume that the attacker sometimes knows a lot of key streams because he has sniffed in some packets in the network. And an attacker could, for example, compute this formula. And this one is interesting because in 2005, Klein could show that this formula has an interesting property because it tends to take the value of the next key byte a little bit more often than all other values which are possible. So this formula can have 256 possible values, and the probability that this one takes the value of the fourth of the next key byte is a little bit higher than all other values, which will be the first byte of the secret root key in a WEP scenario. And it's very easy to compute this formula. So we can find similar functions to determine the next key byte, to determine, or let's say to determine key byte I plus 1 if the first I key bytes of an RC4 key are known. And this is totally sufficient to break WEP, because what you can do is you can just capture a lot of packets, get a lot of key streams, and compute this formula very often. And you have a look at the results, and if you got a lot of packets, then one value, which will be the first secret key byte, will appear a little bit more often than all other values. So you can just, for example, take 100,000 packets, compute this formula, and then you will find out that there will be one value which appears a little bit more often, and this will be the value of your first secret key byte. And then you know always the first 4 key bytes, because the first 3 key bytes of all every packet is the initialization vector, and the fourth key byte is the first byte of the secret root key. And then you can start calculating the second byte of the root key. And this would be totally sufficient to break WEP much faster than Correct does. And we were able to extend it a little bit. We have found the following formula, which has a tendency to take the value of the sum of the first 2 secret key bytes of WEP a little bit more often than all other values, which means that you got the possibility to determine the sum of the first 2 key bytes and determine the first key byte. And after you know the sum of the first 2 key bytes and you know the first key byte, you can find the second key byte, because you can just subtract the first key byte from the sum, and then you get just K4, which is the second byte of your secret root key. And you can very efficiently compute this formula. And we can find similar functions which tend to take the values of the first 3, 4, 5, and 6 key bytes. Or alternatively, we can say if we know the first E key bytes, then we can find a function to determine the first I plus L key bytes of an RC4 key. And this is basically everything we did in our paper. We found these functions, and we wrote an implementation which just takes ARP traffic captured from a network. Then it generates key streams from this ARP traffic, and then it starts calculating the secret key of the network by just computing these formulas and taking the most often appearing value for each formula and then computing the secret key. There are some enhancements. For example, if you got a low number of packets, you can try alternative approaches. For example, you do not just take the most appearing value in these formulas. You take the most and the second most appearing values in these formulas and try to find out if perhaps one of these combinations result in the correct key. And in the last month, we wrote some other enhancements. For example, this can be used